Alright, so let's take a look at a case where we have masses hanging from a pulley. Now, in a lot of times, in a lot of cases, the pulleys may add mechanical advantage if you have a system of pulleys. In this case, if you have a single pulley, it doesn't add any advantage, any mechanical advantage. What it does is redirect the motion. So in this case, we have two masses. M1 is the same as M2, so the masses are equal. And we have the diagram here on the right. And the first step is to, again, figure out what forces are acting on them. So on a system, we're going to have tension in the string. So we're going to have tension here. And we're also going to have tension here. We're going to have gravity acting on the M1 and gravity acting on M2. Now there's no other forces here. We assume that the pulley in this case is frictionless, so there's no friction where the cable goes over the pulley. So one way to solve these sort of questions is to unfold this and make it look like it's in just 1D along a horizontal line. So what we're going to do here is just to come up with some equations, and we're going to solve anything. So let's take a look what we can do. So let's unfold this like this. So we have our M1, M2. Let's label the forces again. Tension, tension, force of gravity, force of gravity. Now notice that these two are the same, right? So keep that in mind when you write your system, your net force equation. So let's pick one direction to be positive. It doesn't matter which way. Let's say positive is that way, right? So anything to the right is going to be positive. Anything pointing to the left is going to be negative. So let's write our F net, or in this case, we can say that this is our y-axis, right? Because originally they were hanging vertically. So we can write our FG2 positive minus T plus T minus FG1 equal the total mass, so MT, times the acceleration. So that's our F net equation. So these two will go away because, again, they're going to be the same. So you're left with FG2 minus FG1 equal to M total times the acceleration of the system. Now, if you think about it, like if you look at the previous diagram here, if the masses are the same and you hang this on the pulley, basically they should not move, so the acceleration should be 0. So let's see if we get that actually from what we have here already. So again, tension will cancel out here. So we have our F net equation right here. Fg2 minus Fg1 equals M total times A. Let's solve this for A. So in order to solve this for A, we need to divide by the total mass. So it's going to be the Fg2 minus Fg1 over the M total. Now Fg2 is made up of the M2 times gravity minus M1 times gravity over M1 plus M2. Now because our M1 equals to M2, we can substitute either M2 with just M1 or M1 with just M2. So let's replace M2 with M1. So I'm going to be rewriting my equation one more time here. So instead of M2, I'm going to write M1 times gravity, M1 times gravity, and here we get M1 plus M1. So as you can see here on the top, these are the same, so they will add to 0. So you're left with 0 on the top and 2m1. But again, 0 divided by anything, still going to be 0. So the acceleration is going to be 0 meters per second squared, which makes sense because, as predicted, if the masses are the same, they should not move. So the acceleration should be 0, which is what we got here. Now let's take the same problem and have different values for our masses. So here's our next example. We have, again, two masses hanging from a frictionless pulley that are released at rest. So find the acceleration of the system and the tension in the string. So remember, to find the acceleration, you need the F net for the system, so using the M total. And when you find the tension, you can use either mass. So whatever mass you pick, usually you want to pick the one with the least number of forces acting on it, because your F net for that mass is going to be simpler. But you can use either mass to find the tension. Now in this case, if you look here, the masses are different. So we know that, from experience, the heavier mass should go down and the lighter mass should go up, which means we can pick the direction or predict the direction of the acceleration. Because I know this is going to go down because it's heavier, I'm going to say my positive direction is going to be this way. So this is going to be my positive direction, and this is going to be my acceleration going that way. So I'm predicting here, I don't know exactly what's going to happen. If it turns out that it's not the case, that just means that my guess was wrong. I'm going to end up with a negative value for the acceleration. If I guessed right, my acceleration ends up being positive, then my guess was correct. So I'm just predicting. The math will actually show me whether my prediction was going to be right or wrong. So anyway, I'm just picking the positive direction, so when I unfold this, I know which way to pick my forces, which are going to be positive, which are going to be negative. So again, we have our tension here, and we have our force of gravity. So let's say this is our Fg1, so this is going to be our M1, and this is our M2. So we're going to have Fg2 here. So let's unfold this, just like we did in the previous case. So we have our M1 of 6 kilograms, M2, so this is our 6 kilograms, 4.0 kilograms here for the M2. Our tension forces are going to be pointing this way. So tension, tension. Now I said that it's going to accelerate in the direction of M1. So this is going to be my Fg1. So again, the positive is going to be this way. Okay, so first, acceleration. So our part A, we need to write the F net for the system. So this is my system. So in this case, positive Fg1, negative tension, positive tension, and negative Fg2, and this equals to the total mass, so mt times the acceleration of the system. Tension forces cancel out, left with Fg1 minus Fg2 equal to the total mass times the acceleration of the system. So we're looking for the acceleration first, so let's rearrange this for A, and you're going to be left with Fg1 minus Fg2 over mt. Let's expand this. So Fg1 is going to be m1 times g minus m2 times g over m1 plus m2. Now again, the masses are not the same, so we can't replace it like we did in the very first example. So we do need to actually plug in the numbers for m1 and m2. We can simplify this, factor out the g if you want, but it's not really necessary. So let's actually, that's a good point. I should show you this, because sometimes I get students to cancel the total mass with one of these. So for example, if you do factor out the g here, because you can factor out the g, you can end up with m1 minus m2 over m1 and m2. Notice here that these will never actually reduce away. You can never cancel out your total mass. Okay, if you end up canceling your total mass, that means your algebra is wrong. You made a mistake somewhere along the way. So just keep that in mind, that you always end up with the total mass at the bottom here. So basically all your masses in your system, you can have more than 2 masses. Of course, you can have 100 masses. They should all be at the bottom here whenever you're finding the acceleration for the system. So the next step is then plug in the numbers to find our A. So 9.8 for the acceleration due to gravity. M1 is 6. M2 is 4.0 over 6.0 plus 4.0. So again, bad mass rules. follow your BEDMAS operations, order of operations. So we're going to end up with 9.8 times 6 minus 4 is 2.0 here, and 6 plus 4 is 10. Notice we gain sig figs on the bottom. So we're going to end up with 2 sig figs on the top, 3 sig figs on the bottom. So our final answer should have 2 sig figs, right? If you don't count our G as a value with sig figs, because it's a constant. So anyway, so 9.8 times 2, we get 19.6. So again, that's going to be 2 sig figs. But I will keep the decimals for the calculation. But I know that I have 2 sig figs on the top. And divided by 10, I'm going to end up with 1.96 meters per second squared. So again, because I'm going to use this value in my tension calculations, I'm going to use this whole number. But if I were to just ask to find the acceleration, I would round it there, right? I would say this is 2.0. Again, I will use this in my part B, so I will use 1.96. But I do keep in mind that the answer should have 2 sig figs. So anyway, that's our part A. We found our acceleration. Part B is asking us to find the tension. Now for this, again, you pick one of the masses, doesn't matter which one. In this case, they both have the same number of forces, so there's no advantage to pick M1 over M2. So whatever the mass you pick, it doesn't matter. So let's say we picked, I don't know, M2, right? We have our 2 forces. Okay, so our F net for this is going to be, let's say this is positive this way. So Fg2 is positive and tension is negative, and this is going to equal to M2 times the acceleration of the system. Actually, hold on. We should stick to the same direction as we picked originally. So let's make this positive this way, which will flip the signs on the forces. Okay, so to solve for tension, I'm going to have to move Fg2 to the right. So T is going to equal M2A plus Fg2. So again, like I said, doesn't matter which mass you pick, you will end up with the same tension. So our M2, actually we can start plugging numbers. M2 is 4 times 1.96. Again, that's going to be 2 sig figs in this first calculation, plus Fg2, which is again the mass of 4.0 times 9.8, which again also is going to be 2 sig figs. So 4 times 1.96 we get 7.84. But again, this would be around 2 sig figs, so 1 decimal. 4 times 9.8, we get 39.2. This also would be rounded to 2 sig figs. So anyway, this is no decimals, this is 1 decimal, so the final answer should have no decimals. Actually, this one here, because 9.8 doesn't count towards sig figs, this should have 1 decimal. You know what? Because basically we're just multiplying by a scalar that doesn't count towards sig figs. So this ends up with 1 decimal. So 7.84 plus 39.2, we get 47.04 or 47.0. So that's our tension. in this case in the rope. Again, in this case, we had a case where there was no friction. And again, the pulleys were hanging from, the masses were hanging from a pulley, left and right side. So let's take a look at a case where we actually have friction, or actually slightly different setup before we get to friction. So here's a case where we have one mass hanging or sitting on the table, and the other mass is hanging from the edge of the table. So notice here the mass is on the frictionless table in this case, and again is attached to the mass that's hanging here. We asked to find the acceleration of the masses, and we asked to find the tension in the rope. So let's label our masses. Let's call this our M1, the one that's hanging from the edge of the table, and this is going to be our M2, the one that's on the table. So as you can see here, in our case, this is going to be frictionless, and the last example will include friction. So let's predict what's going to happen. Let's say that the mass here of M1 will pull the mass that's on the table. So let's say it will accelerate this way, which means this way, M2 will move to the right. So again, I'm just predicting. I don't know whether that's going to be true or not. If it's true, it's going to end up being positive. If it's false, then it's going to end up being just negative. So I'm picking my positive direction. So when I unfold this, I will pick my positive to be to the right. So again, the first step is to find the acceleration of the masses. We're going to write the F-net equation for the system. All right, so here's our M1, which is 6 kilograms, 6.0. And here's our M2, which is 8.0. So the first step is to draw our forces on this. So tension force, force of gravity, Fg1. On M2, we have gravity and normal force. So if we look back here, maybe I should include it here. Here's our Fg2, Fg1. These are going to be our tension force, and a normal force, Fn2. So again, we have normal force here. There's no friction in this case, but we do have the normal force for the M2. So here we're going to add it as well. Normal force, force of gravity in this case is this way. So notice that the gravity from Fg1 is perpendicular to the gravity in M2. And I said the positive direction is going to be this way. So this is going to be my positive. So we have all the forces labeled. Next step is to find the acceleration. So we're going to write our system F-net equation. Okay. So again, Fg1 is positive. This tension is negative, positive, and that's it. These two forces, normal force and Fg2, they're not in the same direction, so we can add it to these two, because in this case they're looking, they're perpendicular in the y direction. These are in the x direction, or in reality these are in the y direction, and this is in the x. So this is going to equal to our m total times the acceleration of the system. So the tension will cancel out, and we are left with just the Fg1 equal to the total mass times the acceleration of the system. So in this case, to find the A, we just need to divide both sides by the total mass. So here we're going to replace our FG1 with M1 times G, and total mass is going to be M1 plus M2. So M1 is 6. M1 plus M2, 6.0 plus 8.0, we get 58.8 over, well, 14. So we get 4.2 meters per second squared. So that's part A. Part B, we had to find the tension. So again, pick the mass with the least number of forces. In this case, M1 seems to be the simpler one. But again, you can also pick M2, just the same. You still can find the tension. Actually, if you look at M2, because we're looking for tension, that would be the only force. So actually, this is the simpler one to use for tension, not this one. So I'm going to pick M2, and let me redraw my free body diagram. Tension, Fn2, Fg2, my sum of forces, or my Fnet. In this case, only tension equal to M2 times the acceleration. So my tension equals to M2 times the acceleration, which in this case it's 8 kilograms times 4.2, we get 34. So that's our tension. Okay, so the most complicated example, let's include friction. Pretty much it's going to be the same thing, but we're adding one extra force, so it's not really that complicated. So let's have the same system, but now we have a force of friction of 25 newtons acting on the 8 kilogram mass. So we said this is our, let's call this our M2 here, and this was our M1. Right, so now we have friction acting on this. So we have, in addition, one more force. Force of friction, let's call this 2, because it's acting on mass 2. We have our Fg2, Fn2, tension, Fg1. All right, well, we have all the forces labeled here. Let's unfold this again and redraw all the vector forces, and then find the acceleration of the masses and then the tension. Now in this case, again, my prediction is going to be the same. I'm going to say that it's going to be going this way. I don't know, this could be wrong. So this is going to be positive, which means this way is going to be positive, right? So when I unfold this, it's going to be positive to the right. And let's see what happens. So again, let's take our masses, unfold it, redraw our forces. So I have our force of gravity, Fg1. We have our tension here. Tension. We have our force of gravity, normal force, and now we added friction. Okay, now the friction force is given as 25 newtons, so we can just make a note here that this is 25 newtons here, 25.0, which is 25. All right, and again, the masses are the same, so this was our 8 kilogram mass, and M1 is the 6 kilograms, 6.0 kilogram and 8.0. All right, so for the acceleration, we need the Fnet for the system. Again, make this positive, so Fg1 is positive. So really, it's pretty much the same steps as before. The one thing maybe slightly more complicated if you're not giving the of friction directly, but you might be given the coefficient of friction. But since you know the mass, you can find the friction because, again, you can find your normal force, and friction force is just mu times Fn. So that'll be one extra step you might have to do. So in this case, we don't need to do that step because we're given the actual value for friction. So we have Fg1 minus tension plus tension, and then minus force of friction. This equals to the total mass and the acceleration of the system. So again, the tension forces will cancel out. You're left with Fg1 minus the friction force equal to the total mass times the acceleration of the system. So we can find Fg1. We know the force of friction. We know the total mass by adding the two masses together. So the acceleration will equal to the m1 times g minus force of friction over m1 plus m2. So m1 times g is 58.8 from previous calculations, and force of friction is 25 newtons. And here we have our 6 and 8 kilograms for the masses. So we get a total of 2.414 meters per second squared. But we're going to end up with, let's see, 3 sig figs on the bottom, 2 sig figs on the top. So we had to round to 2 sig figs. So this is going to be 2.4. Okay, so again, I'm going to use this number in the calculations for the tension, but if you were just looking for the acceleration, that would be 2.4. So part B, let's find the tension. Again, pick one of the masses, pick the simplest one. In this case, both of them have two forces. M1 has Fg1 and tension. M2 has force of friction and tension. So in this case, it doesn't matter which one you pick. Let's say we pick M2 again, just look at it in the previous question, and write our, let's draw the free body diagram for M2. So this is our M2. We're going to have our normal force, force of gravity, tension force, and friction force. So again, positive is this way because we already picked it. And like I said before, this question could be one step extra if you, for example, weren't given the force of friction directly, you were just given the coefficient of friction. So you had to calculate that separately before you can actually plug it in. Now we do care about tension, so in this case we care about the horizontal direction. So we're going to write the F net, let's call this x direction. So we're going to have our tension minus the friction force, m2 times the acceleration of the system that we found, 2.4. So the tension will equal so m2 is 8, 2.414. Again, that's going to be 2 sig figs. So when you multiply these two, it's going to be 2 sig figs plus 25. So we're going to end up with basically the least number of decimals because of the addition. So this gives us 44 newtons. So the tension is 44 newtons. And again, if you did the same math with M1, you should end up with the same tension force. All right, so that's all for tension.